Okay, so welcome everyone. I really appreciate all of you taking some time out of your day to watch this webinar. I'm really excited about the suite of speakers that we have for this webinar and to be able to show some highlights from Clean Air Task Force's recent report that we put out, the Powering the Future report. So with that, I first want to introduce the speakers that we will have today. I will start out by providing some highlights of our recent Powering the Future report that Clean Air Task Force had commissioned. I am Angela Seligman. I am Clean Air Task Force's senior geoscientist. I will then be handing it over to our program director for our Super Hot Rock Geothermal program, Tara Rogers, and she will take us through an overview of project maturity and technological advancements that we have seen in the oil and gas sector. And then finally, I will hand it over to Greg Lavelle, who will take us through a technology overlap overview to point out the overlaps between the oil and gas sector and the geothermal sector. And Greg is with Tidal Wave Technologies, but also importantly, he is the former Chief Technology Officer of ConocoPhillips. So with that, I kind of took us through a brief agenda at the start here, but I will kick us off at the beginning of this webinar with a brief introduction, and then I'll hand it over to our other speakers. And at the end, we are also planning to have a Q&A session and give all of you about 10 or 15 minutes to ask questions. So leading up to that, do feel free to add any questions to the Q&A box throughout the webinar, and that will give us plenty of exciting questions to hand over to our speakers once we get to that Q&A session. But before I really go into an overview of our report, I imagine that many of you have not been introduced yet to Clean Air Task Force. So I want to just take us through a bit of a glance of who Clean Air Task Force is, who we are, and how we work. We are a global environmental nonprofit that was founded in 1996. We have offices in Boston, Washington, D.C., as well as Brussels, with staff working virtually around the world. And the important piece here of what we do is really behind our mission and our vision. Our mission is to push the technology and the policy changes that are needed to achieve a zero emissions, high energy planet, and also importantly, at an affordable cost. And we do this by working as an honest broker and maintaining credibility. That's really our currency. And as we are a nonprofit, we are not the groups out there developing projects or are doing the hard academic research, but we measure our success in manipulating the various levers to move technologies forward. And so you will hear me speaking as well as Tara Rogers. We are in the geothermal team at Clean Air Task Force. So our work and our success is really in the development and the advancement of geothermal technology. And so our success is really based on safely placed terawatts of geothermal power on the grid. And that really gets to the purpose of us having this report commissioned. This is our Powering the Future report, what 50 years of enhanced geothermal teaches us today. You can find that report online now, and in the email that we will send after this webinar, it will also include a link to this report online. Before I really dive into the details of that report, though, I want to just take everyone through a bit of an overview of what geothermal is, as well as what next generation geothermal systems are. So when people typically think of geothermal, they typically think of conventional geothermal systems. This is where you already have your shallow heat source, you already have a reservoir that is containing typically what we think of is hydrothermal fluids in it, and enough fractures or cracks are what we also call permeability throughout the rock to be able to cycle that water through, allowing it to pick up heat and then be brought back up to the surface to generate electricity or provide heat. That is just not available everywhere around the world. And that is where next generation geothermal systems come in. And the two types that I have shown on this slide here are enhanced geothermal systems, sometimes also called engineered geothermal systems. These are shown in the figure in the upper right portion of the slide, as well as closed loop geothermal systems. And these are shown in the lower right portion of the slide. The main difference between these two types of next generation geothermal systems is how you heat that fluid up beneath the Earth's surface. So in both of these types of systems and next generation geothermal systems, we don't have to have that readily available fluid that can flow through the ground through existing permeability. And that allows us to really push next generation geothermal systems to anywhere they are needed. But the main difference between enhanced geothermal systems and closed loop geothermal systems is that in enhanced geothermal systems, we are creating a reservoir underground. So that is allowing us to bring fluid in and then cycle that fluid through a reservoir that is created to pick up heat and be brought back up to the surface and generate electricity. In closed loop geothermal systems, instead of creating a reservoir within the rock underground, we are drilling a series of pipes and then flowing that fluid through the series of pipes. And so the fluid is not actually in direct contact with the rock, but it is still able to pick up that heat while it is flowing through a series of well bores and paths underground that are long enough to pick up that heat, be brought back up to the surface to generate electricity. So with that background, I want to take us through some highlights of our Powering the Future report. And this report is really focused on enhanced geothermal systems and their progress that we have seen over the last 50 years. We had this report commissioned by Jason Lipton with Boulder Energy Advisory, and he really did the legwork to build out this comprehensive database that includes over 100 historical and current EGS projects worldwide. This is built upon over 400 sources, including research reports, press releases, news articles, and personal contacts. And it really quantifies the improvements that we have seen in enhanced geothermal systems technologies over the last 50 years. And the really key highlight here is that enhanced geothermal systems are no longer experimental and that we are seeing projects scaling today. So with that, I'm going to take us through a series of kind of key figures throughout the report, walk everyone through these figures to really set the stage for the progress that we have seen that are identified throughout the report. So as I mentioned previously in the last slide, this report is really based on details from over 100 EGS projects around the world. This is shown in this first figure here that has project year on the x-axis, and then we have two different y-axes on this figure. On the left side, we have the number of projects by continent per year. And then on the right side, we have the cumulative count of those projects. And so this is really showing that uptick in projects in the early 2000s that we've seen, and then getting all the way up to that point of 103 projects. I also want to highlight that all of the projects throughout that are shown in these figures and are included within this report are also in Clean Air Task Force's heat endowment and project map that you can find online. This next figure is looking at the improvements in drilling speeds that we have seen throughout the last 50 years. So on the x-axis on this figure, we are looking at drilling year. And then on the y-axis, this is the ROP, or the rates of penetration. And quite a few of these figures will see some sort of threshold mark. And this is really meant to be a comparative a comparative line in any of these figures that are kind of showing a point where getting to that line is showing some level of success. And so in this one, we have the well cost simplified threshold. This is from Lowry and others back in 2017. And what we can really see from this figure is that recent learning is really being shown. Until recently, we didn't see any projects with an ROP greater than 5 meters per hour, but we are starting to see that in multiple projects more recently. This is shown in the Utah Forge points as well as the Cape Station points. And I also do just want to highlight that what is not shown on this figure, and that is exciting to see, is that this figure is already out of date because we have the recent announcement by Mazama Energy of their ROP reaching up to 30 meters per hour with an average of over 20 meters per hour. In this next figure, we are looking at drilling costs. So on the x-axis, we have the well measured depth in meters, and then on the y-axis, we have the estimated drilling cost per well. And the really key point here, again, we do have these kind of thresholds or scenarios where getting to that lower ideal scenario is really showing that decrease in costs. And we haven't seen a lot of projects get too close to that ideal scenario, but we are starting to see some of these Cape Station points getting much closer to that ideal scenario, showing a decrease in drilling costs over time. And I know that we don't have the year marked on this figure, but we also see in the report that back in an average of from 2021, we had 4 to 5 kilometer wells costing between 10 and $20 million per well. And then even just getting up to 2 years later, the average in 2023 is showing those costs, that average cost decreasing to $4.6 million per well. This next figure is looking at project year on the x-axis, and then now the production temperature on the y-axis. This is in degrees Celsius. We again have a threshold mark. This is at 200 degrees Celsius, and this is a benchmark for commercial power production. It is from MIT's 2006 report, The Future of Geothermal Energy. And what we can really see in this figure here is that although we are seeing an increase in production temperature over time, we haven't quite reached that threshold mark as in terms of an average for commercial power production. But we do see that increase over time. And one of the key highlights from the report is that before the year 2000, the average was just over 100 degrees Celsius. But after the year 2000, we're getting to averages just above 150 degrees Celsius. And so that is showing some really impressive improvements in production temperature over time, but still showing the need for continued improvements in those production temperatures. I do also want to flag for this figure and then also this next one that I will show that there is, of course, wide variability that is driven by things like power production versus direct heat, where not all of these projects are necessarily aiming for higher and higher temperatures. But even with that, we are still seeing that improvement or increase in average production temperature over time. This next figure is looking at well measured depth over time. And so this is really showing that over time, we are getting to wells being drilled to longer and longer distances. So this figure has well measured depth on the x-axis. The x-axis this time is on the top of the figure, and this is because we are looking below ground. So that is the well measured depth in meters on the y-axis going below ground. So that is why these are negative numbers. And then on the x-axis, we're looking at the drilling or recompletion year. And so what we can really see in this figure here is that the average well measured depth is now greater than 4 kilometers over the past 5 years. And this is over 2 times the project averages from the 1970s and the 1980s. So again, showing that we are getting the ability to drill longer and longer wells over time. This next figure is looking at the production flow rates. So again, showing improvements in over time, kind of like we did with the production temperatures. But in this figure, again, we're still not quite up to that benchmark comparative value. And so on this figure, we're looking at project year on the x-axis and then production flow rates in liters per second on the y-axis. That benchmark value is at 80 liters per second. It is again from the 2006 Future of Geothermal Energy report by MIT. And what we can see here is that we are getting an increasing trend over time, getting closer to that benchmark value, but we are still not seeing that average above the benchmark value in terms of production flow rates. This next figure is probably one of my favorites from the entire report. This figure is looking at the primary purpose of these projects over time. So on the horizontal axis, we have the primary purpose of the project. This is going from early stage field research on the left side of the figure over to full scale deployment on the right side of the figure. And then on the y-axis or the vertical axis, we're looking at the project year. And so what this figure is really showcasing is that over time, we have gone from more projects on that field scale stage to now getting to having projects in terms of commercial demonstration and full scale deployment in more recent years. So this is really showing the progress of enhanced geothermal systems over time. Now, the previous slide I said is probably my favorite from the entire report. This figure here is probably the most important from the entire report. Because although we are seeing improvements over time, and we have seen a lot of improvements over the last 50 years, to really get to the true potential of enhanced geothermal systems, there are still more needs in terms of technology development. And we've grouped these into 3 different buckets. This is in technology and operations, market and recognition, and policy and investment on this slide. So these are really showing the primary areas that the technology still needs to really help it reach its full potential to be able to have geothermal technology and geothermal projects anywhere that they are needed, even getting to deeper where we need to drill to deeper and deeper depths to get to that heat source. So going from the left side of the figure over to the right, so starting with the technology and operations, 2 of these points are in terms of the co-production opportunities, as well as a better understanding of the longevity and reservoir decline management of these systems. And in terms of co-production opportunities, these are things like direct use, mineral cogeneration, such as lithium, having an additional co-production opportunity in terms of carbon sequestration or thermal energy storage. And then from the longevity and reservoir decline management, this is really having the ability to understand how quickly we will be drawing that heat from a given reservoir or well over the entire lifetime of the project, which should be decades. The next is in market and recognition. So really showing the full recognition of the unique value of enhanced geothermal systems. This is in terms of their ability to provide baseload, clean, firm sources of electricity anywhere that it is needed without having a volatile source of fuel that needs to be brought in. We also, and I've mentioned this a few times throughout this webinar, being able to expand geothermal to be able to be used anywhere that it is needed, even in those regions where you have to drill to deeper depths. And really to be able to help expand the technology a key aspect is in terms of improving data transparency and standardization to avoid having repeat mistakes from different developers and different projects. And then finally, in terms of policy and investment, this is really along the lines of having more research and regulatory support for the technology so that it can really help to grow and build upon the technology to continue bringing those costs down. So with that, I want to hand things over to our next speaker. This will be Tara Rogers with Clean Air Task Force, and she will talk with us about project maturity and technological advancements. And Tara, I will go ahead and hand it over to you.
Excuse me. Thanks, Angie. You can go ahead and go to the next slide, please. All right. Similar to Angie, I'm of the mindset that there's no point in hiding the purpose. Why are we here? What do I hope you take away from these next slides? Primarily, what you're going to hear is the size of the prize and how quick we are learning. Specifically here, you can see at just 8%, once we are able to extract even 1% of what we're expecting as the potential of geothermal, we're already at 8 times what the world is using today. Go ahead to the next one or click forward. But the real answer, and no, go back one, Angie. The real answer is in the green font above. The investment in geothermal could reach $1 trillion by 2035. What I love about this quote, and you'll find a handful of other pullouts from the IEA's report throughout the rest of these slides, is that IEA estimates the output based on the cost profile and when the power would be dispatched. Said differently, they are projecting a cost reduction profile that is so aggressive that we will see $1 trillion in investment in just 10 years, and of course 2.5 in 2050. Go ahead, Angie. She did talk previously about these things. This I am holding here just to remind the audience that we have the hydrothermal, sort of the historic, what we have done for over 100 years, producing power from these pockets of hydrothermal resources. Now, what we're doing today and sort of the breadth of what Angie presented is in this second, sort of this middle section of using tools, materials, techniques, technologies from the oil and gas industry to make heat extraction possible from dry rock. And ultimately, what we anticipate is again, as the trends show, a press for higher enthalpy systems. And the reason we expect this is because we anticipate that higher enthalpy systems will drive down cost so that it can be competitive in unsubsidized markets with any other source of electricity. So as we move through these slides, I want to remind everybody that for the last 100 years, we have never seen IEA's report predict more than 1% of the total energy mix to come from geothermal. And that is because we were constantly looking at it through the lens of the far left, these pockets of hot water. But going forward overnight, and this came out again, that report came out in November, that we now are projecting a growth of nearly 9%, totaling well over 14% of the total mix by 2050. Go ahead. And Angie, this next set is animated, so please go ahead and just click 2 more times. Here you can see the projection of as we go hotter and we go deeper, more of the Earth's surface now becomes compatible with geothermal energy recovery. Go ahead, one more. Here, Angie also made reference to this in her report that we have commissioned some work with the University of Twente in the Netherlands to estimate where we see resources that are in excess of 374 degrees, so this super hot threshold. And you can poke around on this map, as you can see in the legend to the left, where all of those EGS projects have occurred, both at lower temperatures and at higher temperatures. You can also see some of the heat endowment by country, and those look like those small cut sheets. If a country or a state is in excess of 5 gigawatts of potential or more, you'll find a full cut sheet on where it is and where we expect the opportunity. Like, this is not a prospecting tool, however. Trust that people on this call are much attuned to that. This is purely showing the heat endowment or potential. Go ahead. Now, this particular cut is, in my opinion, exciting because it justifies why we're seeing such aggressive cost reduction projections. And it's primarily in how fast we are learning. Many of these learnings trends will look and feel a lot like what perhaps many of you recall from this shale gas research, and how we are both driving down costs by doing it in the field more frequently, and also targeting higher temperature resources so we have more output from any singular well. Forward. So here I think this was 2021, there was a survey completed, and one of the exciting takeaways here is that more companies are engaged or interested in super hot rock than any of the others now, compared to hydrothermal and sedimentary resources. I think you can see, anecdotally, we can understand how this comes to be in terms of the size of the market. But also, I think we can extrapolate that there is also an understood increased return on investment that comes from increased efficiencies and higher temperatures. If a single well, say operating at 200 degrees Celsius, is projected to put out on average 5, perhaps 7 megawatts each, and a single well at 400 degrees is expected to put out 30 to 40 megawatts, the incremental cost in completing that is more than compensated by its output. And needless to say, this survey is particularly interesting or important as we look to the existing energy market, and to look specifically at the incredible overlap in our skill set and how well we expect that the existing energy market can breach or transition, even just expand into this space without needing to retool. Go ahead. Also, images captured from the IEA report I mentioned earlier here, but while there are many skill sets, we'll call it technical skill sets, that are evident to most, one of the things that gives me the most hope or excitement is also in the project execution and ability to manage risk proactively and intentionally as we grow out. I think you may recall in the project progression slide that Angie showed that we're seeing a lot of commercial scale demonstrations start up now. And this is where, as the opportunity grows quickly, that practiced muscle of project execution will come forward. On the right, you see IEA's estimate on where we're expecting a majority of the cost reductions to come from. And you can see research is a large portion. We understand that to be both in well placement and well field design, but also in material science and being able to capture higher enthalpy systems. Go ahead, Angie. Here, I want to sort of bring it back to the opportunity that many of you may already be generally comfortable with, and what we expected in terms of the learnings from the shale revolution and where we expected costs to come in there versus for geothermal, and specifically for EGS and next generation, where as we As we lower costs, you start to see it looking a lot like these shale wells. However, also taking into consideration that a geothermal well has a very long life, depending on how you operate it. There are many wells, for example, in the well fields in Iceland that have been operating for well over 60 years. Go ahead, Angie. A couple of years ago, we commissioned a research project to attempt to predict where the LCOE might land and how competitive it could be. While I'm happy to go into some of the details of that report and costs, what I found most interesting is its sensitivity. And so here, I wanted to just really point out that magenta line that goes from 7D at a reduction of 70%, all the way down to the on near exact opposite, showing that flow is the most sensitive parameter that we anticipate in terms of driving the LCOE down or up within these EGS projects. Angie, please go forward. And here you can see how flow rates are changing over time. She also presented this, and you'll find it in the EGS report, but this also confirming with a few select projects from 1978 all the way to 2024 at Cape Station. We're already seeing projects and flow rates increase to the level that we anticipate being commercially viable in many markets. Go ahead, Angie. Which gets me to the last slide. Again, sort of coming back to why this is such an exciting opportunity, why we hope we see some of these energy companies expand into the geothermal market. And that is purely on the size of the market and where all it can be, being able to leverage existing leaseholds and perhaps more importantly, existing talent. So in the lowest cost projections or the low cost projection model lined out in IEA, they anticipate a global installed capacity in excess of 800 gigawatts by 2050. I find this very exciting. All right, I think this brings Greg up.
Yes, thank you, Tara. Greg, I'm excited to hand it over to you to talk about the technology overlap between the oil and gas industry and the geothermal industry.
Yeah, thanks, Angela. Uh, what Angela and Tara have asked me to do is provide some real specifics about the types of oil and gas technologies that are having a large impact on geothermal economics. So, starting with this slide, you can see there's really two primary areas where oil and gas technologies are being ported over into geothermal and having a big impact. On the left side of the screen, you're looking at some of the drilling technology elements that are driving down cost, as both Angela and Tara talked about. If you're from the oil and gas industry, a lot of this will look very familiar to you. There's a picture there of a modern high-tech drill rig. I think this is an H&P Flex rig. Frankly, if the mountains weren't in the background, you'd probably think this was out in West Texas somewhere. So bringing over the drilling equipment, changing the bit design. Frankly, the bits designs that were used in geothermal for the last several decades were relatively antiquated compared to what has evolved in oil and gas. So we're switching over from roller cone bits to PDC bits and finding that they are allowing us to increase ROP and run life quite a bit. So big impact there on reducing drilling time. And then finally, something that has been coined or been given the name physics-based drilling really was brought into the geothermal space by a group out of Texas A&M on the Utah Forge project, and really tying together all the different elements of the drilling operations has allowed an incredible amount of optimization. I'll show you some numbers from Utah Forge and the adjacent Fervo site in a minute. Before I get there, I want to talk a little bit about the use of horizontal wells. If you're working in oil and gas, almost anywhere in the world, you realize that most of the wells drilled by industry today are horizontal. That includes the horizontal hydraulically fractured wells that are commonly found in the shale plays in the US, Canada, and now in a few other areas around the world. But also in conventional reservoirs, the majority of wells being drilled are horizontal. For example, if you go to Saudi Arabia, any of the big fields over there, such as Guar, horizontal drilling has been the tool of choice now for the last several decades. So porting over the latest drilling technologies, the latest well types, has really made an enormous impact. Angela, if you go to the next slide, if you could. To demonstrate this, I wanted to just zoom in on what is probably the area that has had the most intense amount of technology transfer, and that's an area in southwest Utah, where the Utah Forge project, it's a government uh, sponsored project designed to prove up EGS technologies. Got started back about a half decade ago, drilling wells, and that's the area where Fervo Energy has also selected to build a half gigawatt scale EGS power generation project. So if you look at the diagram on the left, what you see there is a cross section through the earth indicating the types of wells being drilled and also the types of lithologies being penetrated and the temperature profile. But what is really exciting about this is that not only have we brought over the well designs from oil and gas, but the drilling performance and fluid flow rates being achieved are frankly outstanding. The plot in the middle shows drilling performance for the types of wells being drilled at Forge and Furrow's Cates site. What you see, if you went back more than a half decade, these wells would be probably taking about 150 days to drill with roller comb bits. Uh, Utah Forge and Fervo's Project Red, which was actually a project in Nevada, cut that number a little bit more in half. And today at Cape, Fervo are drilling wells for between 15 and 20 days to almost 15,000 feet measured depth. So laterals of 5,000 feet and depths in the 9 to 10,000 foot range. So an enormous amount of improvement, and you can see the bar on the far right in the middle section there indicates that there's probably more to come. As Tara already talked about, fluid flow rates have increased enormously. I won't go through the details in the plot on the right, but I have put all these numbers in terms that are familiar to oil and gas people, that is in barrels of fluid per day. And what you see here is that in geothermal, we're moving a lot of fluid around the system. A good oil or gas well or a good oil well might be flowing at several thousand barrels a day, maybe up to 10,000 barrels a day. You can see that the wells at Project Cape have a capacity up to almost 70,000 barrels a day. So we're moving enormous amounts of fluid, big hole sizes, long laterals, and that's allowed us to get to these levels. And with further improvements, it's expected that wells delivering over 100,000 barrels of fluid a day will be achievable. Angela, can you go to the next slide? Just zooming in a bit on the EGS element here and the importance of using hydraulically fractured horizontal wells rather than vertical wells. I've got a couple of diagrams here for you to look at. Starting in the top left, the big paradigm change in EGS has been the move from vertical or near vertical wells over to horizontal. The reason this is so important is from what we've learned about how fractures are created in the subsurface when we are hydraulically stimulating a well. We know that going out from a single point, be that a vertical well or a perf cluster in a horizontal well, we are going to get one fracture plane and perhaps some subsidiary planes in a relatively narrow zone around it. You can imagine with vertical wells, if you're trying to connect producers and injectors, this is going to be hard to do. You're going to have to almost precisely know where that fracture is going in order to place the two wells in that same zone of disturbed rock. A lot of dry holes drilled with the vertical wells. And then frankly, the other big problem had been that if you are pumping a lot of fluid into a vertical well, all down one fracture plane, if you will, you're going to very quickly cool down the rocks around that fracture plane, and frankly have a good chance of inducing seismicity because you will be concentrating a lot of fluid in a small area. Look at the diagram over on the right with a horizontal well. We're now able to essentially eliminate the problem with dry holes in geothermal by connecting up numerous fractures between the injectors and producers. So the diagram there shows an injector with two producers on either sides. And, frankly, we can put more water into the injectors, produce more waters out of the producers. And because we're spreading that water out over a larger area, it also reduces the chance of induced seismicity. So we're using modern frac fleets. That's the picture in the bottom left-hand corner. Once again, something that would look perfectly at home in the Permian Basin, the Marcellus, the Vaca Muerta play down in Argentina, or some of the activity underway in the Middle East. And then finally, the diagram on the right is enormously important because what it describes is the uplift in duration of hot fluid production that you can achieve with a horizontal EGS well. The bane of many of the previous EGS projects were you started out at a high temperature because you were flowing the fluid down a single fracture plane or a few fracture planes, you had a fall off in temperature very, very quickly. And that would be demonstrated by the red line there on the graph. Well, with a horizontal EGS well, we're spreading the fluid out over numerous fractures. It pushes the time to thermal breakthrough far to the right. And this dramatically helps the economics. In the top right corner, there is an inset, which is worth looking at. This is from the very first hydraulically fractured horizontal set of wells put in the ground for EGS. That's at Fervo's Project Red. And what you see there is a temperature plot, and it's dead flat. What's shown there is a year of production. They're now up to about 15 months of duration and no decrease in temperature. So, and a really amazing result, and one that bodes very well for the economics of EGS in the long term. Angela, can you flip forward one more slide, which is my last one? I just wanted to give you a sense where hydraulically fractured horizontal wells have been deployed to date, and where people are looking at deploying them. This is a somewhat incomplete map because there is a lot more activity underway, but the Project Red, which I mentioned on the last slide, is located in Nevada. That would be the green star. Cape is in southwest Utah. Angela mentioned the project at the Newberry volcano that Mazama has underway. There has recently been a horizontal drilling project started in Switzerland by Geoenergy Swiss. And there's projects that are in the planning stages in Iceland, New Zealand, and frankly, a whole bunch of other places all over the Western US, and today around many parts of the Pacific Basin and what's commonly called the Ring of Fire. So with that, I'm going to wrap up. I think we have some time for questions. So Angela, let me hand it back to you.
Yes, thank you so much, Greg, and thank you, Tara, as well. I will go ahead and take us into some of the questions that people have been putting into the chat. Do everyone do feel free to add more questions into the chat while we go through this. I think it is very rare that in a planned webinar, everyone sticks to their requested speaking time. So I do want to thank all the speakers here. We actually have about 15 questions available for Q&A, which is what we were hoping for. So do feel free to add more questions in, but in the meantime, I will start to take us through some of these questions that people have been putting in. One of them, Greg, I know you spoke to this a bit in your presentation, and we had a slide early on from the Powering the Future report on the decrease in drilling costs that we have seen over time. One of the questions is around the new technologies that have helped to decrease that drilling cost that we have seen. Greg, I will hand it over to you to maybe speak to some of the new technologies that we have seen develop that have helped to bring those costs down.
Yeah, so the thing which I find really exciting about the drilling cost reduction story is that a lot of what is being done is something you could describe as copy and paste, taking technologies that have already been proven in the oil and gas industry and porting them over into geothermal. That's so much easier than trying to create a new approach from scratch. Obviously, there are some differences that need to be accounted for as you go from oil and gas to geothermal, probably the largest one being the ability to deal with the ultra high temperatures beyond what are normally encountered in the oil and gas space. But I mentioned the use of horizontal wells. Today the longest Uh, Horizontal well that's been used in geothermal is about 5,000 feet. Today in oil and gas, it's almost 30,000 feet, with 15 and 20,000 foot laterals being quite commonly drilled. So, I think that has been a big area of improvement, but an enormous amount of additional upside available. I talked about the changes in the drill bit design, the types of rigs being used. Frankly, there's been a lot of progress being made in mud cooling systems, which allow basically off-the-shelf technologies to be utilized even though the temperatures are extremely hot. So this would be a system whereby the mud is cooled down at the surface, pumped into the well, and the electronics and other parts of a drilling assembly that might be damaged by very high temperatures never see the temperature which is in the reservoir because they're cooled by the drilling mud. So that's probably enough on that. Glad to dive deeper if people have more questions, but a whole plethora of technologies being ported over.
Great, thank you, Greg. There were also a couple of questions about actually about water consumption in these systems and the ability to get permits for these projects that do require a decent amount of water. Um, Maybe Tara, I will hand this over to you, but first, I'll maybe just give a bit of background because it does seem like there's a lot of curiosity on water consumption overall. In these systems. There's for next generation geothermal in general, there's a pretty large range in the amount of water that is consumed in these systems. This can be decreased quite a bit if you have a closed loop geothermal system on the subsurface and the surface. So using binary technology for power production those together can keep the water consumption quite low. And then it varies all the way over to the other side of having much larger water consumption if you have an enhanced geothermal system, depending on how much water is being lost below the surface, as well as then if you have a steam generation or flash system for power production. But there have been quite a few successes that we've already seen to date to help with at least avoiding the use of fresh water in these systems. So just for example, the geysers is using municipal wastewater in their system to keep the pressure up in their reservoir. And then Fervo Energy is also using degraded brackish groundwater for theirs. And so those in general can help with kind of relieving the impacts on communities in terms of freshwater consumption. But of course, you still have to acquire those permits to be able to get the water to use in the system. And Tara, I believe you have at least some insight into this. So maybe I'll hand this over to you.
Angie, I think you've covered most of the most salient points there. Just recalling that there is a distinction between consumption and use in this space, and that there is an effort to use these brackish groundwater, so resources that are not otherwise potable, for the purpose of operating these systems, recognizing that if there is leak off in the subsurface, that it is returning to the same water basin in which it was originally recovered. I think also there is hope that as we move to hotter resources, that the rock itself is naturally less permeable and acts more like an enclosed envelope. And therefore, after the original charge of the system, that you will have less and less leak off as you are engaging in more hotter rocks. But otherwise, I think that this is an important topic, needs further data points, and and just pushing for companies that are engaging in this space to share those data points so that we can predict them and manage them more efficiently.
Yeah, thank you, Tara. Um, Greg or Tara, whoever maybe is most excited about this question, I'll let either of you chime in. There's a question about reservoir decline management overall and long term in EGS systems, and partially whether where they could find the best modeling for reservoir decline management. But I would also like to open this up maybe just a bit more broadly um, for just general reservoir decline management, since this is such an important topic for enhanced geothermal systems. Greg, I see you are already off mute, so I'm going to assume that you are the extra eager one for this question.
Sure, both Taryn and I are eager to answer, but yeah, I actually ended up writing a paper about this topic, which was presented at the Stanford Geothermal Workshop earlier this year. And it turns out that, managing decline in temperature really comes down to being able to characterize the subsurface in a very effective manner and then build a fracture system, which is going to spread the water out evenly through the rock and allow the heat to be extracted in a relatively uniform manner. Some of the challenges that EGS developers are going to face have to do with the presence of pre-existing faults and fractures that may have significantly higher conductivity than what we create in hydraulic fractures or what we are able to produce in a hydraulically fractured system. So trying to avoid naturally occurring faults and fractures is something which should prolong the thermal longevity, also reduces water losses. So I know the water loss questions in the chat, and also reduce chances of induced seismicity. So a lot to learn. Some of the technologies that need to be developed or are being developed are ways to better image the sort of the basement rocks, the granites, the metamorphic rocks that in the past the oil and gas industry has not really paid much attention to. So work being done in that space, and also quite a bit of work being done in using microseismic fiber optics tracers and other tools to characterize the type of fracture system, both man-made and naturally occurring, that is present in any given area.
Angie, if I may also jump in on this, because we're both eager, as Greg pointed out. I do think of this often in the sort of a very classic chemical engineering question. How fast are you going to flow your heat exchanger? If your heat exchanger is via rock or enclosed, you can control the flow and therefore the heat pickup. And that just acknowledging that most operators are anticipating redrills. So there is a point in which you deploy rigs again to identify new areas or create new surface area in which you can recover. I think one of the areas that has not been explored thoroughly is the hypothesis around then the reheat. So this idea that if you were to shut in, say, your first fleet of wells and allow them to heat back up, because ultimately the heat flux from the earth will reheat those wells, and you should be able to recover the heat again in the future. What is the time span? Can you open those wells back up? Which ultimately gets to, I think, a big opportunity in this space, which is more robust modeling, both physics-based modeling, but it's just ensuring that we're also incorporating the heat in the geochemistry in those models, so that perhaps there is a scenario in which, yes, we are anticipating redrills, but is there a world in which we also are, say, moving through them and reopening wells that were previously closed? I think that it's just a brave new world of operation, and we need to see some of these plants operate over longer periods of time for us to be able to model the real decline rate concerns.
Yeah, thank you, Tara. And thank you, Greg, as well. The next question I'm going to take us to is around induced seismicity. So I think we have a couple of questions in the chat about induced seismicity in enhanced geothermal systems. Just briefly at the start, I do want to flag that this is probably one of the biggest points of tension, maybe besides water consumption in these systems that we hear in our conversations with policymakers around the world. But with that, we've also seen really good successes in avoiding induced seismicity from projects when developers really take the time early on, work to understand the geology, the local geology. Are there faults in the region? Are you going to maybe drill into faults that have been active previously? And then also developing some sort of traffic light system where you've developed thresholds based on the local risk, the local concerns of community members in terms of felt induced seismicity, where you have these points where you start to pull back as maybe induced seismicity is getting to larger and larger magnitudes. And so really taking care to be able to control the system and avoid having a large felt event. But with that, I also want to just flag that I know we all get concerned about induced seismicity, but in the development of a reservoir, some really small induced seismicity is important for those of you who have needed to be able to kind of, so we can say, see underground by generating microseismicity that can help us to monitor the development of the reservoir. So there's really this balance between keeping the induced seismicity below a level that can be felt on the Earth's surface, while also using those really small micro earthquakes that can't be felt on the surface to using geophysical methods to image the reservoir. Um, Greg or Tara, did you want to add anything to those points on induced seismicity?
I think you did a good job of covering it, Angela. The thing I'd add, I guess, is that once again, there's a lot of copying and pasting going on. We've learned a lot over the last really 50 years in the oil and gas industry about how to manage induced seismicity. It really comes down, as you said, to characterizing, monitoring, and mitigating and managing any problems that occur. On the monitoring side, the area I was talking about at Fervo's Cape site has hundreds of microseismic uh, monitoring devices deployed. So a lot of information being gathered so far. No particular problems at that site. So I think we're on a good trajectory, and we just need to keep learning and managing.
All right, thank you, Greg. I think we have time for maybe one more question, and Greg, I'll hand it to you. There's a question on, and I think you may have put a first answer in the chat to this, but about the thermosiphoning driven circulation in these systems, and how if that is required to maintain flow, and then the pumping energy requirement, and how significant that is to maintain the flow through these enhanced geothermal systems. Or is that a good question for you
Yeah, it's a
there,
good
Greg?
question. Anytime you're pumping cold water down into the earth and it heats up, you are going to get some lift, if you will, out of the system. But for most EGS systems, because you're going through fractures which have relatively low conductivities, you are going to need to pump the fluid down at a high enough pressure to basically allow it to round trip around the entire loop there. The heating of the fluid does give you some benefit, but not something that would be relied on for completing the process. Closed loop, however, I mean, because you're going down a wellbore, one of the benefits there is you don't have to use as much pumping power, since you have, basically a infinite amount of conductivity in the wellbore. So, yeah, good question. I think something that is a benefit, but not something sufficient. And then on the amount of power required, that's generally referred to as parasitic load, and it does decrease the amount of power generated. You can think about it as a subtraction from the amount of output from the power plant, and usually that runs in a range of a few percent of total power output.
Yeah, thanks, Greg. And thank you, Tara, as well. I do see that we are at the top of the hour. I know that we did not get to all the questions in the Q&A. But I really appreciate everyone's engagement in this, and a huge thank you to Greg and Tara for speaking on this webinar. We will follow up with an email from for all participants, including those who registered but were not able to make it. It will include a recording. And do feel free to reach back out to that email if you do have any follow-up questions that weren't answered during this webinar. But thank you so much, everyone, for your time. And thank you for your interest in enhanced geothermal systems and geothermal in general.